Models of sequential circuits. There are two models, namely Mealy model or Mealy finite state machine and Moore model or Moore finite state machine. It differs only in the way the output is generated. In Mealy model, output is a function of both the present state and the input. Whereas in Moore model, output is a function of only the present state. We can compare Mealy and Moore model. In Mealy model, output depends both upon the present state and the present input, whereas in Moore machine, output depends only upon the present state. Mealy has fewer states than Moore, and generally Moore has more states than Mealy. Mealy reacts faster to inputs. They generally react in the same clock cycle, whereas in Moore machine, more logic is required to decode the outputs, which results in more circuit delays. They generally react one clock cycle later. Sequence detector is also called as pattern detector. These are the applications of pattern detector: vending machine, lift, or a mobile. Let's design a circuit that detects a sequence of 3 or more consecutive ones in a string of bits coming through an input line. That is, the input is a serial bit stream. Let's see how to draw the state diagram using Moore model. Let's assume the input bits are arriving in this particular fashion. This is just an example. So the initial state is going to be S0. When the input is going to be 0, it will remain in the same initial state S0, and the output will remain to be 0. We represent the output inside along with the state in the Moore model. When the input is going to become 1, it will move on to the next state called as S1, and the output will still remain to be 0. If at all the input is going to be 0 at the point of S1, it will return back to the initial state of S0 and the output will be 0. But if the input is going to be 1, it will move to the new state called S2 and the output will still remain to be 0 because we have received only 2 consecutive ones. If the input is again going to be 0, it will again return back to the initial position and the output will be 0. But if the input is going to be 1, it will move on to a newer state called S3 and the output will become equal to 1. It's because we have received 3 consecutive ones. So the output is going to become 1. And if again the input is going to become 0, it will start fresh from the initial state S0. But if the input is going to be 1, it will remain in the same state where we will receive the output as 1. So this is a state table. Based on the state diagram, we can draw the state table. And we can use a D flip-flop, and for this D flip-flop, from the K map, we can derive the expressions for DA, DB and the output Y. DA is obtained as AX plus BX, DB is obtained as AX plus B complement X and Y equals AB. So with the derived expressions, we can use D flip-flop and draw the logic diagram. So we have got two flip-flops, so this is going to be DA and this is going to be DB, and the clock is going to be common because this is a synchronous sequential circuit. And we also have Y, which is going to be the output of the circuit. Obviously, X is going to be the input for the circuit, where this is going to be the input stream. Here is where we are going to receive the input bits. And this is the logic diagram for the sequence detector, and it is also called as pattern detector. We'll move on to the next problem to design a sequential circuit which has one input and one output. When input sequence 110 occurs, the output becomes 1 and it remains 1 until the sequence 110 occurs again, in which case the output returns to 0. The output remains 0 until 110 occurs a third time, etc. Input and output. Say if the first sequence of 110 appears, the output will become 1 and it will remain as 1 until the next sequence of 110 appears. Once the second sequence of 110 appears, the output becomes 0 and the output will still remain 0 until the third sequence of 110 appears. Once the third sequence of 110 appears, the output becomes 1 and it will remain as 1 until the fourth sequence of 110 appears, where the output becomes 0, and this pattern gets repeated. Let's see how to design the circuit. Now let's do it in the Mealy model because the output is going to vary. Let's assume the first state to be A, initial state, and when the input is going to be 0, it will remain in the same state and with the output as 0. But if the input is going to be 1, it will move on to the next state B and the output will still remain 0. And from here, if the input is going to be 0, it will go back to the initial position A and the output will become 0. But if the input is going to be 1, it will move to the third state C and still the output will be 0. If the input is going to be 0 again, the output will be 1. Why? Because we have received the sequence 1, 1 and 0. So the output has become 1 and it has moved into the state D. Now, if the input is going to be 1, it will remain in the same state. After reaching state D, if the input is going to be 0, the output will continue to be 1. And if the input is going to be 1, the output will still remain 1 and it will go to E. And from E, if the input is going to be 0, it will go back to state D and the output will remain to be 1. But if the input is going to be 1, then it will move on to the next state F and the output becomes 1. And from F, if the input is going to be 0, it will move to state A, the initial state with the output as 0. But if the input is going to be 1, the output will remain as 1 and it will remain in the same state. So thus we are able to detect the sequence, and this is a state diagram for the sequence. Now we can observe that there are 6 states. So we can name them states as 000, 001, 010, 011, 100 and 101. We have observed there are 6 states and we are going to use D flip-flops, and the input is going to be X and the output is going to be designated as S. This is the excitation table which we have obtained from the state diagram and the characteristic table of D flip-flop. We've got 6 states, so we need 3 D flip-flops, and we can represent the present state like this: next state, the flip-flop input and the corresponding outputs. These are the logical expressions. Using the K-map, we have derived the expressions for D0, D1, D2, the input equations of the flip-flops, and the output S. From the expressions derived using the K-map, we can draw the logic diagram for the 3 flip-flops D0, D1 and D2. The input is going to be X, and the clock signal is given common for all the 3 flip-flops because this is a synchronous sequential circuit. And this is the logic diagram for the final output S.